The estimation approach that is most commonly associated with structural equation modeling programs is maximum likelihood estimation. This particular estimation approach makes the assumption that your observed variables that are included in the model exhibit multivariate normality. When this assumption is not met, this can yield biases with respect to the chi-square test and the goodness of fit indices that are derived from the computation of the chi-square test. Moreover, the standard errors can be off as well, so this can yield biases when you're testing statistical significance associated with individual parameters within your model. So within this video, I'm going to just briefly demonstrate how you can obtain the Satorra Bentler chi-square test or scaled chi-square test and adjusted standard errors when you have a situation where there may be an absence of multivariate normality. Before I do that, though, I do want to just kind of give a little illustration of how you can assess for multivariate normality in Stata. So what I have, or what I've done, is I've called up a data set. I'm just going to go under Data Editor and go to the Stata data file, and I'm just going to go under Browse here, and you can see I have a set of measured variables and values for each case below. So what I want to do is I want to just first assess the variables that I'm going to include in my model for multivariate normality or lack thereof, and then I will illustrate how I can utilize the Stata graphical user interface to create a path model and test it and request the Satorra Bentler chi-square test and the adjusted standard errors. So I'm going to begin by typing in MV test normality, and then the name of the variables that are going to be included in my model. So I'm going to include up here dogma, and actually I can just drag this down here and it will show up certain, incog, in structure or need for structure. Also, I'm going to include fear. Actually, I'm not going to include fear. I'm going to include perceived threat and aggressiveness. So I'm going to include those. Then next, I'm going to have a comma, and then I'm going to specify several options. So I'm going to ask for univariate, space, bivariate, stats, and then in parentheses all. So in terms of this structure here, you can see MV test for normality, so multivariate test for normality. These are the variable names that are going to be, they represent obviously the variables in my model. I'm asking for univariate statistics, bivariate statistics, and then just really all of the different types of output that I can get in relation to these variables. So when I press enter, I get, you can see right here, here's my command, and so I've got test for univariate normality. So the PR, these are just probability values associated with skewness and kurtosis. So what I would be looking for in terms of an absence of univariate normality on any of these dimensions is a p-value that would be less than 0.05. So you can see that for dogma, these p-values are greater than 0.05. Same for certain, incog, in structure, perceived threat, same. But then we have aggressiveness here, and you can see that there's evidence of a lack of normality on that particular variable. We also have some tests of bivariate normality, and so you have each pair of variables, so dogma and certain. And so again, over here we're looking for p-values that would be less than 0.05, which would suggest an absence of bivariate normality. So dogma certain, that p-value is greater than 0.05, dogma need for cognition, greater than 0.05, greater than 0.05. Dogma and perceived threat is less than 0.05. Dogma and aggressiveness is definitely less than 0.05 p-value. So we have, as you scroll down, you can see that there are several significant tests for with respect to bivariate normality, and statistical significance is actually indicating a deviation from bivariate normality. Just like up here, a test of a significant test result would indicate that you have a deviation from univariate normality. We'll click on more, and so we have different additional tests. So we've got Mardia's test for multivariate test for skewness. You can see that we have statistical significance here because we have a p-value less than 0.05. Also for the for both of these two indices here, we have p-values that are less than 0.05. The Mardia kurtosis test is not statistically significant, but overall it looks like that we have some problems with respect to multivariate normality for those particular variables. So in testing out my path model, this seems to be a good situation where we might want to utilize the Satorra Bentler scaled chi-square test and adjusted standard errors. So to draw out the basic path model, I'm going to go to Statistics, SEM, go to Model, Building, and Estimation. And I kind of discussed this in another video, but just really quickly, you can see over here we've got various icons, and these are basically buttons, and so we can draw out our path model using these buttons. So I'm going to press here, and basically I have three exogenous variables. So you can see I'm just kind of draw 1, 2, and you can see that there's the third one. So as long as I don't click this little button right here, then I can just keep drawing these rectangles out. And these are basically these are all the rectangles or boxes are used to represent observed variables. So now I'm going to click this little button, click off, and next what I can do is I can basically draw out well, I'll just go ahead and ask for the variables and put them in. So to name the boxes, I'm just going to highlight one. I can go up here, and then I can just basically use a little arrow and then down, and then put the variable name in. So I'll do the same for this one. Okay, so at this point, I'm going to click here, just kind of click it out, and then I'm going to draw my paths in the model. So I'll go certain to dogma, hypercognition to dogma. I can make this a little prettier if I took a little bit more time. And then just going to draw this one right here. This probably is not very theoretically driven. I'm just kind of putting stuff in. But the main point is that we would specify the causal relations or proposed causal relations based on some theoretical conception. And what you'll notice is that the boxes that have arrows pointing to them, this little term right here, this is called a disturbance. This will show up. And this just represents variation in the variable that's being predicted that is unexplained by the predictors in the model. I'm also going to add the double-headed arrow here so that we can have correlations among our exogenous variables in the model. Okay, so there's a basic path model. And so next I want to estimate the parameters in the model. So I can go to Estimation, click on Estimate, and you can see the method is maximum likelihood. That's that default I was telling you about. And I can go to Standard Errors Robust, and then here when I scroll down we have the Satorra Bentler estimator. So I'm going to click on that and then on OK. So now you can see that in our model we have basically these are all unstandardized path coefficients because I didn't ask for standardized in the output. And so if I click on any given path, though, it's going to give me the unstandardized coefficient, the standard error, z-value, and then a probability value. So where it says underneath coefficient, these are unstandardized estimates. Where it says this is basically standardized estimates right here. So we have the standardized path coefficient, a standard error, z-value, and a p-value associated with that. So at any rate, I'm going to go into my output file and kind of scroll up a bit here, and you'll notice that I'm getting the unstandardized regression coefficients or path coefficients for each of the paths. If we look under structural, these are the proposed relationships, and these are the paths that are being estimated. So these are basically these are the same estimates that you will see in the path diagram and also shown over here. Moreover, you can see that we have the p-values associated with each of those, with tests of each of those parameters. You'll notice up here it says Satorra Bentler standard error. So in other words, these standard errors have been adjusted for non-normality or lack of multivariate normality with our observed variables. So these are the z-values and the p-values associated with each coefficient. So if I click back and go back here, I can go to estimation, go to goodness of fit, and overall goodness of fit. Typically I just ask for all of the above and click on OK. And so now when I look in my output, you'll notice that I've got the likelihood ratio chi-square. So this is the test based on normal theory. So this is assuming that our variables are normally distributed or exhibit multivariate normality. Down below, you've got the Satorra Bentler scaled chi-square, and so this is the value here. And so basically, you're looking at the chi-square test to see if it's statistically significant. So generally, we're looking for p-values that would be that at 0.05 or less than 0.05, which would indicate statistical significance. And statistical significance for the chi-square test is actually indicating that your model is demonstrating poor fit to the data. So like I said, we're going to go ahead and stick with the Satorra Bentler chi-square because we're assuming that our observed variables are not multivariate normally distributed. So instead of relying on the likelihood ratio chi-square, which is the normal theory chi-square, we're going to use this estimate right here. Then you'll notice, so based on this, and actually based on both of them, you can see that there's evidence that our model is not fitting the data particularly well. You'll notice down below, you've got the RMSEA and then a Satorra Bentler RMSEA. So basically, this is the RMSEA value that we would want to consult. If we're assuming that our data are not multivariate normally distributed. So this reflects the Satorra Bentler adjustment that we saw up above with this particular chi-square test. So what we're looking for here are values that are 0.05 or below. That would suggest more optimal levels of fit. Below 0.08 would suggest at least acceptable fit. And so in this particular case, this value is definitely above 0.08, which would suggest poor fit. You'll notice that, if we were using the likelihood ratio chi-square, then we would be using this RMSEA up here. But like I said, we're going to assume our data are not meeting the assumption of multivariate normality. So we're going to stick with this Satorra Bentler test right here, this RMSEA value here. And then we'll click on more here. We'll use the Satorra Bentler comparative fit index and Tucker-Lewis index. So these are adjusted based on the adjustments that we saw above with the Satorra Bentler chi-square test. And so basically with these, we're going to be looking for values that are 0.90 or above, which would suggest good model fit. And it turns out that both of these values are less than 0.90, which these would also be suggesting poor model fit. And then the last thing that we can look at is the standardized root mean squared residual. And with this particular index, we're looking for a value at 0.05 or below. And here, this value is greater than 0.05, so this is actually suggesting a poor model fit. So based on the Satorra Bentler chi-square test, the adjusted RMSEA based on the Satorra Bentler correction, the CFI and TLI, again reflecting that correction, and also the standardized root mean residual, or root mean square residual, our model does not appear to demonstrate good fit to the data. Nevertheless, you can see also that the same general conclusion would have been observed had we just utilized the standard chi-square test, the standard RMSEA, the standard CFI and TLI, and obviously the standardized root mean squared residual. But again, there can be cases where this adjustment is more pronounced, and so you can end up with different conclusions between the normal theory method and the Satorra Bentler method. So for that reason, although it didn't make any difference in this particular output, it's still important to keep in mind this option when you're dealing with data that are not exhibiting multivariate normality.